Hello, in this lecture we will find out the radius of the circle using two different methods. In the drawing we have a circle. The center of this circle is at this point, point O. Line segment AB equals to 6 units. Line segment AD equals to 18 units. Line segment BC equals to 13 units. This angle BAD equals to 90 degrees, and this angle ABC equals to 90 degrees also. Our mission is to find out the radius of this circle. So we'll start with the first method. In the first method we will make a construction. From the point C we go perpendicular on AD. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point C and AD as E. By doing this construction, we actually created a quadrilateral ABEC. Quadrilateral ABEC has 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the fourth angle in total. And the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees. So actually, quadrilateral ABEC has 4 right angles. Therefore, quadrilateral ABEC is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But it is given us the question that AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that side BC must be equal to side AE and rectangle ABEC. But it is given us in the question that side BC equals to 13 units, therefore side AE must be also equal to 13 units in its length. Okay, what is the length of this line segment ED? From the drawing it is very easy to see that ED equals to AD minus AE. AD equals to 18 units, AE equals to 13 units, 18 minus 13 is 5. So ED equals to 5 units. In the next step, we will join points C and D together by a straight line. By joining points C and D, we created the green right triangle and the green small right triangle, ECD. In the next step, we will implement the Pythagoras theorem of this green right triangle, ECD. Here by PT is abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right green triangle is DC. Therefore, the square of the hypotenuse is DC squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to EC squared plus ED squared. So DC squared, that is the square of the hypotenuse of the green triangle, must be equal to EC squared. EC equals to 6 units, therefore EC squared is 6 squared, that is 36, plus ED squared. ED equals to 5 units, therefore ED squared equals to 5 squared, that is 25. In conclusion, we found out that DC squared equals to 36 plus 25. So DC squared, the square of the hypotenuse, equals to 36 plus 25 is 61. Here we take out all of this equation and we get that DC equals to the square root of 61 units. Okay, so we found out that the hypotenuse of the great small triangle BC is equal to the square root of 61 units. In the next step, we will join points B and D together by straight line. By joining points B and D, we actually created the right triangle ABD. In the next step, we will implement the Pythagoras theorem on the right big triangle ABD. Okay, so this right big triangle ABD. By PT is the abbreviation for Pythagoras theorem. So the square of the hypotenuse equals to the sum of the squares of the perpendiculars in the right triangle ABD. The hypotenuse is BD, therefore the square of the hypotenuse is BD squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB squared plus AD squared. So we actually found out that according to the Pythagoras theorem, in the right big triangle ABD, BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse, equals to AB squared. AB equals to 6 units, therefore AB squared equals to 6 squared, that is 36, plus AD squared. It is given us the question that AD equals to 18 units, therefore AD squared equals to 18 squared, that is 324. So in conclusion, we found out that BD squared, that is the square of the hypotenuse of the right big triangle ABD, it is equal to 36 plus 324. 36 plus 324 equals to 360. So BD squared equals to 360, so we substitute 360 by 36 times 10. And we get that BD squared, the square of the hypotenuse of the right triangle ABD, equals to 36 times 10. Here we'll take a root out of this equation and we get that BD equals to the square root of 36 times 10. The square root of 36 is 6, so we can take 36 out of the root and we get that BD, that is actually the hypotenuse of the right big triangle ABD, equals to the square root of 36 is 6 times, inside the root we left only with 10, times square root of 10. So BD equals to 6 times square root of 10 units. Here, the hypotenuse BD equals to 6 times square root of 10 units. In the next step, we'll find out the area of this triangle BDC. Repeat again, we'll find out the area of this green triangle BDC. If the squared bracket is the sign for the area, it means the area of triangle BDC, the green triangle. The area of any triangle, and especially triangle BDC, equals to the base of the triangle times the height to the base over 2. Here I must emphasize that the height to the base must create 90 degrees with the base. So the area of the green triangle BDC, equals to the base of the triangle. We will choose the base as BC. So the base is BC according to our selection. Times the height over 2. In the next step we will find out the height of the green triangle BDC. In order to find out the height to the base, we will extend side BC by a straight line, and from point D we will go perpendicular on the extended side BC. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D in the extended BC as point F. By doing this construction, we created a quadrilateral ABDF. This quadrilateral has 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. And therefore, quadrilateral ABDF that has 4 right angles, it is a rectangle. Okay, so I write it down. Quadrilateral ABDF is a rectangle. Why? Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AB must be equal to side DF. You can write here that side AB equals to side DF. And it is also given us in the question that side AB equals to 6 units. Okay? So we can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive that DF equals to 6 units also. So DF, what is actually DF? DF is the height to the base. Why? Because side DF creates 90 degrees with the extended base BC. So actually found out that the height to the base that creates 90 degrees with the base, with the extended base, it equals to 6 units in its length. Now we can easily find out the area of the green triangle, triangle BDC. So the area of the green triangle, triangle BDC, equals to the base of the triangle, the base, we choose the base as BC, and we know that the base BC equals to 13 units, so we substitute BC by 13. Times the height. We just right now found out that the height to the base that creates 90 degrees with the base equals to 6 units, so the height equals to 6 units over 2. So actually found out that the area of the green triangle, triangle BDC equals to 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. Okay, so the area of the green triangle, triangle BDC equals to 39 square units. Okay. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. So this will be actually rule number 1. Rule number 1 is true in any circle. So the circle that I will draw here could be any circle. The center of this circle is at this point, point O. And this circle blocks triangle ABC. This is a triangle ABC that is blocked by this circle. So whenever you have a triangle that is blocked by a circle, you can use rule number 1. So write the rule down. If triangle ABC, this is triangle ABC, we know that side AB equals to A units in its length, the length of side BC is B units and side AC equals to C units in its length. So if triangle ABC is blocked, triangle ABC could be any triangle, is blocked by a circle. What is the definition of a triangle that is blocked by a circle? Actually, only if all the three vertices of the triangle touching the circle, we can say that the triangle is blocked by a circle. Otherwise, the triangle is not blocked by a circle. Here, you can see that this vertex is blocked. It touches the circle at point A. This vertex of triangle ABC touches the circle at point B, and finally, this vertex of the triangle touches the circle at point C. Therefore, we can definitely say that this triangle is blocked by the circle. And now, whenever you have a triangle that is blocked by a circle, the following equation will be true. We'll define the radius of this circle as capital R, here OM equals to capital R according to our definition. So the radius of a circle that is blocked, the radius of a circle that blocks a triangle, in this case it is capital R. Then the radius of this circle that is equal to capital R will be equal to A times B times C, that is the multiplication of the side lengths of the triangle by each other, the multiplication of the triangle that is blocked by the circle by each other, over 4 times the area of this triangle, triangle ABC. And because of the fact that triangle ABC could be any triangle, this rule is true for any triangle that is blocked by a circle. Okay? We actually can implement rule number 1 in our drawing. Why? Because in our drawing, the green triangle BDC, is blocked by this circle. Why? Because this vertex of the triangle BDC touches the circle at point B. This vertex of triangle BDC touches the circle at point C, and finally this vertex of the green triangle touches the circle at point D. Therefore, we can definitely say that this triangle BDC is indeed blocked by this circle. So, I write it down. The green triangle BDC is blocked by this circle. We will define the radius of this circle as capital R, here, that is to say here OM, that is the radius of this circle. According to our definition, it is equal to capital R. And because of the fact that the green triangle BDC is blocked by this circle, we can implement here rule number 1. According to rule number 1, the radius of the circle that blocks the green triangle, that according to our definition it is equal to capital R, will be equal to the multiplication of the side lengths of the triangle by each other. That is to say, it is BC times CD of DC times BD over 4 times the area of the green triangle, triangle BDC. I'll repeat again. Because of the fact that the green triangle, triangle BDC is blocked by this circle, we can implement it rule number 1. According to rule number 1, the radius of this circle that is blocked by, that blocks the triangle, the green triangle, that is to say capital R, that is the radius of this circle according to our definition, will be equal to the multiplication of the side lengths of the triangle by each other. That is to say it is BC times DC times BD over 4 times the area of the green triangle, triangle BDC. According to rule number 1, of course, so capital R equals to BC equals to 13 units in its length, side BC, side CD or DC equals to the square root of 61 units in its length, and finally side BD of the green triangle equals to 6 times square root of 10 units in its length. All divided by 4 times the area of this green triangle, triangle BDC, and we have already found out that the area of the green triangle BDC, it is equal to 39 square units. So that is actually also the answer to the question. We actually found out the radius of this circle, and the question is to find out the radius of the circle. So in the next step we will just simplify this expression by dividing both the numerator and the denominator by 13. So in the numerator we have 13, and 13 over 13 is 1, so 13 will get cancelled, and we left only in the numerator with the square root of 61 times the square root of 10 times 6 over, in the denominator we have 4 times 39. 39 over 13 is 3. So in the denominator we left with 4 times 3. That is to say, the radius of the circle that blocks the green triangle, triangle BDC, capital R, equals to the square root of 61 times square root of 10 times 6 over 4 times 3 is 12. Here we will divide both the numerator and the denominator of this expression by 6, and we get that the radius that we are looking for equals to the square root of 61 times the square root of 10. 6 over 6 is 1, so 6 will get cancelled. So in the numerator we have we left only square root of 61 times square root of 10 over 12 over 6 is 2. Okay, so the radius of the circle equals to the square root of 61 times square root of 10 over 2. According to the algebraic identity that the square root of A times square root of B equals to the square root of A times B, we get that the square root of 61 times the square root of 10 equals to the square root of 61 times 10 over 2. So the radius of the circle that we are looking for equals to the square root of 61 times 10 is 610 over 2. So the radius of this circle, capital R, equals to either the square root of 610 over 2 units, or in terms of numbers it is equal to 12.349 units. Okay, so we finished with the first method. In the next step I will present to you how to find out the radius of this circle according to the second method. So in the second method, in the first step, we'll do the same thing that we have already done in the first step. That is to say, from point C, we will draw perpendicular on AD. So this angle equals to 90 degrees. And this angle will be also equal to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. Inside quadrangle ABEC we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. I will not repeat on the reason. We have already done it in the first method. So inside quadrilateral ABEC we have 4 right angles, therefore quadrilateral ABEC is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say side AB equals to side EC. But it is given us in the question that side AB equals to 6 units, therefore side EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that side BC equals to side AE. But side BC equals to 13 units, therefore side AE must be also equal to 13 units in its length. The length of side ED, as we already done it in the first method, it is ED equals to AD minus AE. AD is 18 units, AE is 13, so AD minus AE is 18 minus 14, that is 5. So we have already done those things in the first method. From now on, we continue with the second method. In the second method, from point O, that is the center of this circle, we will draw perpendicular on BC. Again, from point O, that is the center of this circle, we will draw perpendicular on chord BC. This is called BC. So actually, this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and BC as capital N, and we will define the touching point of the perpendicular from point O and AD as M. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. So this will be actually rule number 2. Rule number 2 is true in any circle, so the circle that I will draw could be any circle. Here the center of the circle is at this point, point O. And we have here chord BC. That could be any chord. And from the center of this circle, that is to say from point O, we will draw perpendicular on BC. So this angle equals to 90 degrees, and this angle it is also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and BC as M. According to this rule, rule number 2, if a perpendicular or you can find out that the perpendicular from the center of the circle in this case, the center of the circle is at point O, so I write it down. To any chord here, chord BC could be any chord, bisect the chord. That is to say, in this case it means that BM equals to MC. So whenever you draw a perpendicular from the center of a circle towards any chord, it will bisect the chord. In this case, the perpendicular OM on BC bisects chord BC, that is to say BM equals to MC. And we can actually implement this rule number 2 in our drawing. Well, because in our drawing we have perpendicular ON that exists from the center of the circle, that is to say from point O towards chord BC, and according to rule number 2, it will bisect the chord BC, that is to say BN equals to NC. So I'll write it down. In our original drawing, we have perpendicular ON that exists from the center of this circle, that is to say from point O you will add that the perpendicular ON is from the center of the circle. It must be from the center of the circle, of course, according to rule number 2. So the perpendicular ON to chord BC, this is chord BC, bisect chord BC, according to rule number 2. Bisect chord BC, that is to say BN equals to NC. According to the new rule number 2. Okay. So, in the next step, we will focus on quadrilateral ABMN. Inside quadrilateral ABMN, we have 1, 2, 3 right angles. Therefore, the forefinger must be also equal to 90 degrees. And therefore, quadrilateral ABMN is 4 right angles, and therefore, quadrilateral ABMN is a rectangle. So I write it down. Quadrilateral ABMN is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to AM equals to BN. AM equals to BN. According to the rule that the opposite sides of a rectangle are equal to each other. Likewise, we focus in the next step on the lower quadrilateral MNEC. Inside this quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, the forefinger must be also equal to 90 degrees. Quadrilateral MNEC that has 4 right angles. It is a rectangle. So I write it down. Quadrilateral MNEC is a rectangle. And again, we know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So to summarize what we did until now, according to rule number 2, we found out that Bn equals to Nc. But according to the rule that the opposite sides of a rectangle are equal to each other, we found out that Bn it is also equals to Am. So you can write here that Bn equals to Am. And according to the same rule that the opposite sides of a rectangle are equal to each other, we found out that NC it is also equals to ME. So we can write here that NC equals to ME. From this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. That is to say, this side AM equals to side ME. Okay? In the next step, we will extend line segment AD until it touches the circle, and we'll define the touching point of the extended line segment AD and the circle SF. By doing this construction, we created here chord FD. FD is a chord. Okay? A couple minutes ago, from point O, we drew perpendicular on chord BC. ON is perpendicular to chord BC. So ON as a perpendicular, it is absolutely a straight line. Okay? And according to all the old rule number 1, the sum of the angles on one side of a straight line is equal to 180 degrees. Here, the sum of those two angles, AB is a straight line. If we focus on the upper side of the straight line AB at point K, here the sum of the angles must be equal to 180 degrees. That is to say, those two angles must be in total they must be equal to 180 degrees. AKL plus BKL must be equal to 180 degrees. So we can implement here rule number 1. ON is perpendicular, it is absolutely a straight line. So if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have at the upper side of ON at point M? We have this angle that is a right angle, it is equal to 90 degrees, plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule number 1. Therefore, the missing angle here must be also equal to 90 degrees. Likewise, we will focus on the lower side of the straight line ON at point M. Here, according to the same rule, rule number 1, the sum of those two angles must be equal to 180 degrees. So which angles we have? At the lower side of ON at point M, we have this angle that is equal to 90 degrees. Plus the missing angle, in total, they must be equal to 180 degrees according to rule number 1. Therefore, the missing angle, it is also must be equal to 90 degrees. So actually, we have here line segment OM perpendicular to chord FD. Okay, so I write it down. OM line segment OM that exits from the center of the circle, that is to say from point O, is perpendicular to chord FD. Therefore, we can implement here rule number 2. And according to rule number 2, the perpendicular OM bisects chord FD. Okay? So, FD has been bisected by OM, that is to say FM equals to MD. FM equals to MD according to rule number 2. Okay, FM equals to MD. FM, it is equal also to FA plus AM. So we can substitute FM by FA plus AM. And it is equal to MD. Here MD, it is also equals to ME plus ED. MD equals to ME plus ED. So we actually found out that FA plus AM equals to ME plus ED. But we have only found out that AM equals to ME. AM equals to ME. And because of the fact that those two line segments are equal to each other, we can cancel them out and we left only with FA that is equal to ED. FA equals to ED. But we have already found out that ED equals to 5 units. Here we can write down that ED equals to 5 units. And from this equation, FA equals to ED equals to 5, we will derive that FA equals to 5 units. FA equals to 5 units. In the next step, we will extend side BA until it touches the circle, and we will define the touching point of the extended side BA and the circle as P. Here we can actually implement the old rule number 2 in our drawing. I will remind you the old rule number 2. According to the old rule number 2, with chord AB, this is called AB intersects with chord CD, this is called CD, it's point O, then AO times OB equals to CO times OD, again AO times OB equals to CO times OD. We actually can implement the old rule number 2 in our drawing. Why? Because in our drawing we have chord FD. This is chord FD that intersects with this chord PB at point A. For that reason, we can implement, we have two chords that intersect with each other in our drawing. Therefore, we can implement here the old rule number 2. So I will write it down. So, here, chord FD. intersects with chord PB at point A. Repeat again. Chord SD intersects with chord PB at point A. That is to say we have two chords that intersect with each other. For that reason, you can implement here the old rule number 2. According to the old rule number 2, we get that FA times AD equals to PA times AB. Repeat again. According to the old rule number 2, FA times AD equals to PA times AB. FA equals to 5 units, AD equals to 18 units, PA is the missing 9 segments, so we leave it as it is. Times AB equals to 6 units. In conclusion, we found out that according to the old rule number 2, 5 times 18 equals to PA times 6. If we divide this equation by 6, and we get that PA, the 9 segment, the missing 9 segment equals to 5 times 18 over 6. So PA equals to 18 over 6 is 3, and 3 times 5 is 15. So we found out that PA equals to 15 units. And right here that PA equals to 15 units. So in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. This will be actually rule number 4. Actually, according to rule number 4, whenever you have two chords that are perpendicular to each other, you can use a certain formula in that case. Okay? So I'll draw the circle, that could be any circle. The center of the circle is at this point. We define the center of this circle here as point E. So we have chord AB, this is called AB. That intersects with chord CD at point O. This is called CD. Actually, in other words, you can say that chord AB is perpendicular to chord CD. Those two chords are perpendicular to each other. That is to say, they create between them 90 degrees at the intersection point. We will define the intersection point as point O. So, if, according to rule number 4, chord AB is perpendicular to chord AD They're actually perpendicular to each other at point O. And the intersection point that we defined as point O. We define the radius of this circle as capital R. Here EM equals to capital R according to our definition. So whenever you have two chords that are perpendicular to each other, then the following equation will be true. The equation is as follows. Then 4 times R squared equals to AO squared plus OB squared plus CO squared plus OD squared. Repeat again. This drawing we have two chords that are perpendicular to each other, that is to say chord AB perpendicular to chord CD at point O. Therefore, whenever you have two chords that are perpendicular to each other, the following equation will be true, that 4R squared, R is the radius of the circle, equals to AO squared plus OB squared plus CO squared plus OD squared. We actually can implement this rule number 4 in our drawing. Why? Because in our drawing we have two chords that are perpendicular to each other. That is to say, chord FD is perpendicular to chord PB. Here they create at the intersection point, that is to say, it's point A, 90 degrees. Therefore, they are perpendicular to each other, and therefore we can implement here rule number 4. So I write it down. So in our original drawing, chord FD is perpendicular to chord AB. I'll repeat again. In our original drawing, we have chord FD that is perpendicular to chord PB. They are perpendicular to each other at point A. Chord FD is perpendicular to chord PB at point A. This is point A, the intersection point. Therefore, we will define the radius of this circle OM equals to capital R. Therefore, according to rule number 4, we get that 4R squared, again R is the radius of the circle, will be equal to FA squared plus AD squared plus PA squared plus AB squared. Okay, again, because of the fact that in our original drawing chord FD is perpendicular to chord PB, we can implement here rule number 4. According to rule number 4, 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared. So 4R squared, R is the radius of this circle, equals to FA squared. FA equals to 5, therefore FA squared equals to 5 squared, that is 25, plus AD squared. AD equals to 18, therefore AD squared equals to 18 squared, that is 324, plus PA squared. PA equals to 15, therefore PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6, therefore AB squared equals to 6 squared, that is 36. In conclusion, we found out that 4R squared equals to 25 plus 225 is 250, plus 324 plus 36 is 360. So 4R squared equals to 250 plus 360 is 610. So we found out that 4R squared equals to 610. We'll divide this equation by 4. And we'll get that R squared equals to 610 over 4. Here we'll take a root out of this equation, and we'll get that the radius of this circle, capital R, equals to the square root of 610 over 4. That is to say, capital R, the radius of the circle, equals to the square root of 610, and the square root of 4 is 2. So we found out that the radius of this circle, capital R, equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. So we finished with the second method. In the next step, I will summarize the lecture. We'll start with the first method. In the drawing we have a circle. The center of this circle is at this point O. In addition, we have here line segment AB that is equal to 6 units. Line segment AD equals to 18 units. Line segment BC equals to 13 units. This angle BAD equals to 90 degrees, and this angle ABC equals to 90 degrees also. Our mission is to find out the radius of this circle, the value of the length of OM, that is the radius of this circle, that we define as capital R. So in the first step, we did the construction, that is to say, from point C, we do perpendicular on AD, so this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD as E. So we created a quadrilateral ABCE. This quadrilateral has 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees, and therefore quadrilateral ABC that is 4 right angles, it is a rectangle. But we know that the opposite sides of a rectangle are equal to each other, that is to say AB equals to EC. And it is given us the equation that AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that BC equals to AE. But it is given us the equation that BC equals to 13 units, therefore AE must be also equal to 13 units. Then we found out the length of line segment ED. From the drawing, it is very easy to see that ED equals to AD minus AE. AD equals to 18 units, AE equals to 15 units, so AD minus AE is 18 minus 13, that is 5. So ED equals to 5 units. Then we join points D and C together by straight line. By joining points D and C, we created the main small triangle EDC. In the next step, we implemented the Pythagoras theorem on the great small right triangle EDC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is a relation for Pythagoras theorem. In the great small triangle, the hypotenuse is DC. Therefore, the square of the hypotenuse is DC square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC square plus ED square. So in conclusion, we found out that DC square equals to EC square plus ED square in the right green triangle ECD. So DC square, that is the square of the hypotenuse, must be equal to EC square. EC is 6, therefore EC square is 6 square, that is 36, plus ED square. ED equals to 5, therefore ED square is 5 square, that is 25. In conclusion, we found out that DC square equals to 36 plus 25. 36 plus 25 is 61, so we found out that DC square equals to 61. Then we took out of this equation and we found out that DC, that is to say the hypotenuse of the great small triangle EDC, equals to the square root of 61 units. Here, DC equals to the square root of 61 units. Then we joined points B and D together by straight line. By joining points B and D, we created the right triangle ABD. Okay, this white big triangle ABD. Then we implemented the Pythagoras theorem on the right white big triangle ABD. Here by PT is a relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the big triangle ABD is BD, therefore the square of the hypotenuse is BD square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB square plus AD square. In conclusion, we found out that according to the Pythagoras theorem, in the right triangle ABD, BD square equals to AB square plus AD square. AB equals to 6, therefore AB square is 6 square, that is 36, plus AD square. AD equals to 18, therefore AD square equals to 18 square, that is 324. So in conclusion, we found out that BD square equals to 36 plus 324 is 360. So BD square equals to 360. Then we substituted 360 by 36 times 10. So BD square equals to 36 times 10. Here we took out of this equation and found out that BD equals to the square root of 36 times 10. The square root of 36 is 6. Therefore we can take 36 out of the root, and in conclusion we found out that BD equals to 6 times, inside the square root we have only 10 left. So BD equals to 6 times square root of 10 units. That is to say the hypotenuse BD on the right triangle BD equals to 6 times square root of 10 units. In the next step we found out the area of the green triangle, triangle BDC. The area Here the square brackets is the sign for the area. The area of any triangle, and especially the area of triangle BDC, equals to the base of the triangle times the height to the base over 2. Here I must emphasize that the height to the base must create 90 degrees with the base. So the area of our green triangle, it is not a right triangle, it is BC. So choose BC is the base of the green triangle times the height over 2. Then we found out the height of the green triangle BDC. We did the construction here. We actually extended side BC by straight line, and from point D we do perpendicular on the extended BC. That is to say, this angle equals to 90 degrees, and this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D and the extended BC as F. So actually, because of the fact that line segment DF is perpendicular to the extended side BC, DF, it is actually the height to the base, to the extended BC, okay? So in the next step, we found out the value of the height DF. Here we have quadrilateral ABDF. Quadrilateral ABDF has 1, 2, 3 right angles. Therefore, the fourth angle, this angle must be also equal to 90 degrees. Therefore, quadrilateral ABDF that has 4 right angles, we relate to it as a rectangle. Quadrilateral ABDF is a rectangle. Yes, out here. Quadrilateral ABDF is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. Here, AB equals to DF. It is given us the equation that AB equals to 6, so we can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive that DF is also equals to 6 units. Here DF equals to 6 units, therefore the height to the base is equal to 6 units. Now we can easily find out the area of the green triangle BDC. According to the formula, the area of the green triangle BDC equals to the base times the height over 2. The base is BC, and BC equals to 13 units, therefore we substitute BC by 13 times the height. We just now found out that the height equals to 6 units, so we substitute the height by 6 over 2. So the area of triangle BDC, the green triangle, it is 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. In conclusion, we found out that the area of this green triangle BDC equals to 39 square units. In the next step, I presented to you a new rule that is actually rule number 1, and we implemented rule number 1 in our drawing. So actually, according to rule number 1, if triangle ABC, that could be any triangle, is blocked by a circle, then the following equation is true. So whenever you have a triangle that is blocked by a circle, you can use rule number 1. And according to rule number 1, the following equation will be true. Here, side AB equals to units in its length, side AC equals to 3 units in its length, and side BC equals to B units in its length. And the radius of this circle, OM, equals to capital R. So you can find out the radius of a circle that blocks a triangle by knowing only the side lengths of the triangle that is blocked by the circle and the area of the triangle that is blocked by that circle. That is to say, the radius of this circle, capital R, will be equal to A times B times C. That is the multiplication of the side lengths of the triangle ABC by each other over 4 times the area of triangle ABC. Here I must emphasize that this triangle ABC is blocked by a circle, or in general a triangle is blocked by a circle only and only if all the 3 vertices are touching the circle. Here you can see that this vertex of the triangle touches the circle at point A, this vertex touches the circle at point B, and this vertex of triangle ABC touches the circle at point C. Therefore, we can definitely say that this triangle ABC is blocked by the circle. If not all the 3 vertices touching the circle, then the triangle is not blocked by a circle. Okay, so again, the radius of this circle that blocks triangle ABC equals to A times B times C over 4 times the area of triangle ABC. We can actually implement this rule number 1 in our drawing. Why? Because in our drawing we have the green triangle BDC that is blocked by this circle. Why it is blocked by this circle? Because of the fact that this vertex of triangle, the green triangle, touches the circle at point B, this vertex touches the circle at point C, and this vertex of triangle BDC touches the circle at point D. Therefore, we can definitely say that the green triangle BDC is blocked by this circle, and therefore we can implement here rule number 1. So repeat again. Triangle BDC, the green triangle, is blocked by this circle, therefore we can implement here rule number 1. According to rule number 1, the radius of this circle that we defined as capital R will be equal to the multiplication of the side lengths of the green triangle by each other, that is to say BC times CD times DB, BC times CD times BD over 4 times the area of the green triangle BDC. Okay, here BC equals to 13 units in its length, CD equals to the square root of 61 units in its length, and finally BD equals to 6 times square root of 10 units in its length. Okay, and all divided by 4 times the area of the green triangle BDC. But we have already found out that the area of the green triangle BDC equals to 39 square units. Okay, so the answer to the question is that the radius of this circle, capital R, equals to this expression. Here we simplify this expression by dividing both the numerator and the denominator of this expression by 13. In the numerator we have 13, 13 over 13 is 1, so 13 will get cancelled, and we left in the numerator only with the square root of 61 times square root of 10 times 6 over 4 times 39. So we divided the denominator also by 13, so it is 4 times, and 39 over 13 is 3. So the denominator we left only with 4 times 3. 4 times 3 is 12. So in the denominator we have only 12. In the numerator we have square root of 61 times square root of 10 times 6. Here we divided both the numerator and the denominator of this expression by 6. 6 over 6 is 1, so in the numerator we left only the square root of 61 times square root of 10. And 12 over 6 is 2. So the radius of the circle equals to the square root of 61 times square root of 10 over 2. According to the algebraic identity, that the square root of a times b equals to the square root of ab, we get that the square root of 61 times square root of 10 equals to the square root of 61 times 10, all divided by 2. 61 times 10 is 610. So we found out that the radius of this circle, capital R, equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finish with the first method. Then I presented to you how to find out the radius of this circle according to the second method. In the second method, in the first step, we did the things that we have already done in the first method, so I will repeat on them shortly. From point C, we draw perpendicular on AD. This angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AD is E. By doing this construction, we created here quadrangle ABEC. Inside quadrangle ABEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, quadrangle ABEC has 4 right angles. And therefore, quadrangle ABEC is a rectangle. And we know that the opposite sides of the rectangle are equal to each other. That is to say, AB equals to EC. But it is given as a question that AB equals to 6 units, therefore EC must be also equal to 6 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE. But BC equals to 13, therefore AE must be also equal to 13. And what is the value of ED? ED equals to AD minus AE. That is to say, it is 18 minus 13, that is 5. So, we did all those things in the first method. From now on, we will continue with the second method. In the second method, from the center of this circle, that is to say from point O, we do perpendicular on chord BC. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and chord BC as N, as capital N. Then we define the touching point of the perpendicular from the center of the circle, that is to say from point O and AD as capital M. Then I presented to you a new rule that is actually rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, whenever you draw perpendicular from the center of a circle towards any chord, it will bisect the chord. Here, from the center of the circle, that is to say from point O, we draw perpendicular on chord BC, that could be any chord. Here, this angle equals 90 degrees, and this angle equals 90 degrees according to our construction. So whenever you draw perpendicular to a chord, it will bisect the chord. We have perpendicular OM, and according to this rule number 2, perpendicular OM bisect chord BC. That is to say, BM equals to MC. Okay, so we can actually implement rule number 2 in our drawing. Why? Because in our drawing, from the center of this circle, that is to say from point O, we have perpendicular ON on chord BC. And according to rule number 2, it will bisect chord BC, that is to say BN equals to NC. So, I've written again that perpendicular ON from the center of the circle, that is to say from point O to chord BC, bisect chord BC. That is to say BN equals to NC according to rule number 2. Okay, then we focused on quadrilateral ABMN. Inside quadrilateral ABMN, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees. Therefore, quadrilateral ABMN, that has 4 right angles. It is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. Repeat again. On the other, ABMN is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. Likewise, we focused on the lower quadrilateral MNEC. This quadrilateral, we have 1, 2, 3 right angles. Therefore, this fourth angle must be also equal to 90 degrees, and therefore quadrilateral MNEC, that has 4 right angles, it is a rectangle. Repeat again, quadrilateral MNEC is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So, we can summarize what we did until now. According to rule number 2, we have already found out that BN equals to NC. But according to the rule that the opposite sides of the rectangle are equal to each other, we also found out that BN is also equal to AM. BN equals to AM. So we can write here that BN equals to AM. And according to the same rule that the opposite sides of a rectangle are equal to each other, we found out that NC equals to EM. So we can write here that NC equals to EM. So from this long equation, AM equals to BN equals to NC equals to ME, we will derive that AM equals to ME. AM equals to ME. Here, side AM equals to side ME. Then we actually extended line segment DA until it touches the circle at point F. By doing this construction, we added chord FD. And here, a couple minutes ago, we drew perpendicular from the center of the circle, that is to say from point O towards chord BC. That is to say, ON is perpendicular to BC. ON as a perpendicular is absolutely a straight line. And according to rule number 1, that the sum of the angles from one side of a straight line is equal to 180 degrees. So if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule number 1. So which angles we have? And the upper side of ON at point M, we have this angle that is equal to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees according to rule number 1. Therefore, this missing angle must be also equal to 90 degrees. Likewise, then we focus on the lower side of the straight line ON at point M. According to the same rule, the sum of the angles here must be equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees, according to rule number 1. So this angle equals to 90 degrees plus the missing angle. In total, they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees. So in conclusion, we found out that OM is perpendicular to chord FD. Why? Because this angle equals to 90 degrees, this angle equals to 90 degrees, therefore OM, line segment OM that exists from the center of this circle, that is to say from point O, is perpendicular to chord FD. Therefore we can implement here rule number 2. According to rule number 2, it bisects chord FD, that is to say FM equals to MD. I repeat again. OM, that is from the center of this circle, that is to say from point O, is perpendicular to chord FD, and according to rule number 2, whenever you have a perpendicular from the center of the circle towards the chord, it will bisect the chord. That is to say, OM bisects chord FD. If OM bisects chord FD, it means that FM equals to MD. Okay, FM equals to MD. FM equals to MD according to rule number 2. But FM, it is also equals to FA plus AM. So we can substitute FM by FA plus AM, and it is equal to MD. Here you can see that MD, it is equal to ME plus CD. MD equals to ME plus CD. So we can substitute MD by ME plus CD. In conclusion, we found out that FA plus AM equals to ME plus CD. But we have already found out that AM equals to ME. So here AM equals to ME, the two chords are equal to each other, therefore we can cancel them out. So we cancel them and we left only with FA that is equal to ED. So here FA equals to ED. But we have already found out that ED equals to 5 units. So we can write here that ED equals to 5 units, and from this equation FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. Here, line segment FA equals to 5 units. In the next step, we extended side BA until it touches, by circle, until it touches the circle at point P. And then we implemented here the old rule, rule number 2. According to the old rule, rule number 2, whenever you have two chords that intersect with each other, in this case we have chord AB that intersects with chord CD at point O, then the following equation will be true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement rule number 2 in our drawing, because in our drawing we have two chords that intersect with each other. We have chord FD that intersects with chord PB at point A. I repeat again, in our original drawing we have chord FD that intersects with chord PB at point A. Therefore we can implement here rule number 2. According to rule number 2, we get that FA times AD equals to PA times AB. I repeat again, FA times AD equals to PA times AB according to the old rule, rule number 2. Okay, FA equals to 5 units. AD equals to 18 units. PA is the missing line segment, so we leave it as it is, and AD equals to 6 units. In conclusion, we found out that 5 times 18 equals to PA times 6. We divided this equation by 6 and found out that PA equals to 5 times 18 over 6. 18 over 6 is 5, and 18 over 6 is 3, and 3 times 5 is 15. So we found out that PA equals to 15 units. Yeah. PA equals to 15 units. In the next step, actually, I presented to you a new rule, rule number 4, and we implemented rule number 4 in our drawing. According to rule number 4, whenever you have two chords that are perpendicular to each other, then you can use a certain formula. You can use this formula. So here we have chord AB that is perpendicular to chord CD. Why they are perpendicular to each other? Because they create with each other 90 degrees at the intersection point O. And we know that the radius of this circle it is equal to capital R, EM equals to capital R. So whenever you have two chords that are perpendicular to each other, you can use the following formula in order to find out the radius of the circle. And the formula is that 4R squared, R is the radius of the circle, equals to AO squared plus OB squared plus CO squared plus OD squared. Okay? So actually can implement this new rule number 4 in our drawing. Why? Because in our drawing we have also two chords that are perpendicular to each other. Here, chord FD is perpendicular to chord PB, therefore we can use here rule number 4. Because of the fact that chord FD is perpendicular to chord PB, why? Because they create here 90 degrees at the intersection point A, we can use here rule number 4. I repeat again, in our original drawing we have chord FD that is perpendicular to chord PB at point A. They create between them point A 90 degrees, therefore they are perpendicular to each other, therefore we can use rule number 4. We define this, the radius of this circle as capital R, that is to say OM equals to capital R, and the formula that we can use here according to rule number 4, it is actually 4R squared, R is the radius of this circle, equals to FA squared plus AD squared plus PA squared plus AB squared. Okay, according to rule number 4, because we have here two chords that are perpendicular to each other, we can use the following formula that 4R squared, R is the radius of the circle, equals to FA squared plus AD squared plus PA squared plus AB squared. So here FA equals to 5, therefore FA squared equals to 5 squared, that is 25. Plus AD squared, AD equals to 18, therefore AD squared equals to 18 squared, that is 324. Plus PA squared, PA equals to 15, therefore PA squared equals to 15 squared, that is 225. Plus AB squared, AB equals to 6, therefore AB squared equals to 6 squared, that is 36. So in conclusion, we found out that 4R squared equals to 25 plus 324 plus 225 plus 36. 25 plus 225 is 250, and 324 plus 36 is 360. In conclusion, we found out that according to rule number 4, 4R squared equals to 250 plus 360. 250 plus 360 is 610. So 4R squared equals to 610. We divided this equation by 4 and we found out that R squared equals to 610 over 4. Okay. Then we took a root out of this equation and we found out that R equals to the square root of 610 over 4. That is to say, R equals to the square root of 610 and the square root of 4 is 2. So in conclusion, we found out that the radius of this circle according to the second method, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay, thank you very much.